So this video elaborates the concept of stiffness matrix method. So the indeterminate beams can be analyzed using matrix methods also. So here we have a number of terminologies commonly used in this method. Consider a three-span indeterminate beam of length L1, L2, L3. L1, L2, L3 are the spans. And to consider the joint load W and delta. W is the joint load, delta is the joint displacement at possible supports. So at fixed support, there is no deflection occurs. So we should not assume the displacement at the fixed support. So the next intermediate joint as well as end simply supported can be assumed with the joint load and joint displacement. And the common coordinates which we are going to calculate in this problem is the member end force and member end displacement. So P is the member end force and U is the member end displacement. So each and every member should have two member end coordinates at the both the ends, P1 U1, P2 U2 for the first member, P3 U3, P4 U4 for the second member, P5 U5, P6 U6 are the third member. So totally 6 coordinates used to represent the member end coordinates. So again I am repeating, the possible joint should be assumed with joint load and delta. At fixed support, there is no possibility of deflection, so we should not assume the joint load and delta. There is no need of calculating joint load here. So generally, your problem will be given with the loadings. Any loadings, it can be a point load and it can be a UDL throughout this span. So the joint load W can be calculated using the fixed end moment values. If it is a central point load, then the anticlockwise fixed end moment on the left side, that is WL by 8, that is minus WL by 8. Here it is plus WL by 8. For the UDL, it is WL square by 12. WL square by 12. Here clockwise WL square by 12. For the varying span load, if you consider it is with the AB distances, the anticlockwise moment of WAB square by L square. Here WB A square by L square of clockwise. So anticlockwise represent the negative value and clockwise represent the positive value. Here negative and positive. Here negative and positive. If you sum up the values according to the magnitude of the load, if you sum up, for example, plus 30 minus 20 means the resultant direction will be along this direction because this is the maximum value of plus 30. WL square by 12 is minus 12 means the resultant fixed end moment will be in this direction. Similarly, you have to judge the resultant fixed end moment direction. So I just assume the direction. For example, I am assuming the net fixed end moment values. First one, this is fixed end moment value. Here you can calculate net fixed end moment value with the direction. So it is positive, here it is negative, here it is positive, anti-clockwise and clockwise. At the fixed support, you can also mark the net fixed moment value. Here the joint load W is the opposite property of the net fixed end moment. That is, first of all, I put the direction opposite to that net fixed end moment direction. So I am putting opposite direction to the negative fixed end moment. Why it is opposite direction? I am going to explain. The fixed end moment is the internal parameter. Fixed end moment is the internal parameter. Joint load is the external parameter. External load applied on the beam at the joint. So it is an external parameter. Then the internal parameter is the effect. External parameter is the cause. So we have to consider the opposite sign for the internal parameter to get the external joint load. That is why we are assuming the opposite direction of this load. Okay, this is all about the joint load calculation. If it is 30 minus 20, it is 10, then the resultant moment is 20. Here it is 30. For example, I am giving the value. Then the opposite direction of these values should be considered for the joint load. And if you write W1, W2, and W3 in matrix format, here it is anti-clockwise, so minus 10. Here it is clockwise, so plus 20. And here it is anti-clockwise, so minus 30. So you calculate the net fixed end moment value and consider the opposite sign of the net fixed end moment value to assemble the joint load matrix. So this is all about joint load calculation. And coming to this matrix analysis, first of all, we are going to uh, consider the relationship between the member end displacement to the joint displacement, because member end displacement is the member end coordinates, where delta is the joint coordinate. So I am going to derive a relationship between member end displacement to the joint displacement. For that, I am going to write the equation for U1. U1 is assumed at the joint A, but there is no delta here. There is no delta 1, there is no delta 2, and there is no delta 3. So U1 can be represented with 0 delta 1, 0 delta 2 plus 0 delta 3. Okay. Similarly, U2 can be represented as, if you look at U2 parameter, it is active in the delta 1 displacement. It is active in the delta 1 displacement, but it is not related to delta 2 and delta 3. So you put delta 1 plus 0 delta 2 plus 0 del 3. If you consider U3, it is related with the delta 1 joint displacement. It will give the effect on delta 1. U3, remember, end displacement will be occurred due to delta 1 deflection joint displacement. So delta 1 is active. The other joint displacements are considered to be 0. U4, we are considering this member end property. Delta 2 is available for U4 as well as U5. Other joint displacements are 0. So 0 del 1 plus del 2 plus 0 del 3. Similarly, U5 equal to 0 del 1 plus del 2 plus 0 del 3, and U6 equal to, the U6 is the last coordinate which is available for del 3 only. So other joint displacements are 0 plus del 3. So again we are checking U1 is the starting first coordinate which is not giving effect on del 1, del 2, del 3. So all the coordinates are 0 for the joint displacement. U2 is active for del 1, U3 is active for del 1, U4 is active for del 2, U5 is active for del 2, and U6 is active for del 3. Now we are going to assemble in the format of matrix. So how U1, U2, U3, U4, U5, U6. So it is varying according to the loading conditions. So you should give this type of parenthesis. And here del 1 del 2 and del 3. So this is also varying according to the loading condition. In between, it can form a matrix of box type of parenthesis. That is, if you should get the first row of this equation, u1 equal to, you multiply 0 with del 1 and 0 with del 2 and 0 with del 3, then you will get this first row. So u1 equal to 0 del 1 plus 0 del 2 plus 0 del 3. Similarly, you should arrange the other rows. u2 is equal to 1 into del 1. So 1 into del 1, 0 into del 2 and 0 into del 3. u3 is 1 into del 1, 0 into del 2 and 0 into del 3. u4, 0 into del 1, 1 into del 2 and 0 into del 3. u5, 0 into del 1, 1 into del 2, 0 into del 3. u6, 0 into del 1, 0 into del 2, 1 into del 3. So we are going to have some important relationship uh, from this set of matrix equation. So we got u1, u2, u3, u4, u5, u6. I am representing as u matrix, which is equal to, we got 0, 1, 1, 0, 0, 0. Totally 6 coordinates should be present. 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1 into the joint displacement L1, L2, L3. So I can represent this matrix as A matrix, which is referred to the displacement transformation matrix. Already I have given the terminology. So this A can be represented as displacement transformation matrix. So it gives the relationship between member end displacement to the joint displacement. It gives the relationship between the member end displacement to the joint displacement. Similarly, we can arrive for the conclusion for the joint load to the member end force, because U and delta are the quantity referring the displacements. W and P are the coordinates referring the forces and moments. So we can form a relationship between W and P, which gives the transformation matrix of B, which is the force transformation matrix, which is the force transformation matrix. So here we can also conclude the displacement transformation matrix, which is equal to transpose of force transformation matrix, and the force transformation matrix is the transpose of the displacement transformation matrix. It is also one of the important conclusion. So you keep, this is equation number 1, here it is equation number 2. This equation number 2 can be further reduced to W matrix equal to, instead of B, we can substitute A transpose with the box bracket and multiplied with the membrane forces. If this is equation number 2. So, in addition to this, we are going to relate the equation for member end force P with the U. Actually, in beam analysis, in slope deflection equation, we have an equation MAB equal to M bar AB plus 2EI by L 2 theta A plus theta B minus 3 del. So you neglect these items, sudden moment and supportive settlement in this equation. Then A2B gives 4EI theta A by L plus 2EI by L into theta B. 2EI by L into theta B. So here we can understand 4EI by L is the moment at A, whereas half of the moment is carried over to B as 2EI by. So the basic definition for stiffness equal to the force per unit displacement or moment. Here I can represent with okay, we keep it as u or delta. We can give delta or small delta, whatever may be the terminology. So here k equal to force per unit displacement or moment per unit rotation, where theta equal to 1 and also here delta equal to be considered as 1. So in this equation, if you consider this 1, here also the rotation is 1, then the simplified term, that is moment at A, will be 4EI by L when theta equal to 1. At the same time, the moment at B occurs is 2EI by L. So, in clear format, if a member is subjected to only rotation, then the stiffness value K equal to moment per unit rotation, which is also equal to moment, because theta equal to 1 means K is directly equal to moment. What is the moment value? At A it is 4EI by L. Here it is 2EI by L. Actually, we are applying theta equal to 1 here, and we are analyzing the parameter at both the ends. So the load is applied at 1 and the effect is measured at 1, or otherwise the rotation is applied at 1 and the effect is measured at 1. So we can give the stiffness influence coefficient Kij. So normally it is measured as Kij, where J is the load position, can be meant for load position. Here I is the effect position. So K11 equal to 4EI by L, where 2EI by L, here the load is applied at 1, the effect is measured at 2. So this is nodal point 1, here it is 2. You consider this one. So K11 is 4EI by L, K21 is 2EI by L. In the same manner, you consider a unit rotation is applied here, theta equal to 1 is applied here, so that this moment will be 4EI by L, here will be 2EI by L. So we can name it as the rotation is applied at 2 and the moment, that is stiffness, is measured at 1. So K22, here the rotation is measured at the node 2, but the effect is measured at the node 1. So I can assemble a stiffness matrix, that is member stiffness matrix K. So K1, K2, K3 for the number of members. So small k is referred to a member stiffness matrix, that is 4 similar, it is and be assembled as K11, K21, K12 and K22. Okay. So K11 is 4EI by L, K21 is 2EI by L, here it is 2EI by L, 4EI by L. Okay. So this is the stiffness matrix for a beam element. Stiffness matrix for a beam element. If you are having 3 spans, this matrix is for one single span. If you are having 3 spans, for the first span here it is 2 by 2 matrix. Another for 2 spans it is 4 by 4 matrix. If it is 3 span, so you will get 6 by 6 matrix of overall stiffness matrix. Okay. For our problem, the overall stiffness matrix is equal to 6 by 6. So let us derive this equation, where I am going to derive the relation between P and U, where P is the member force in the unit of kilonewton meter only. That is, it is directly referred to the moment. And U is referred to the rotation. So P is referred to 4EI by L at A and 2EI by L at B. So this is referred to member end displacement, so member end forces. So in this relation, we can formulate the equation where the first one P1, and you try to draw the supports. Here it is P1, U1, P2, U2, P3, U3, P4, U4, P5, U5, P6, U6. So P1 is the leftmost end for the span L1. So here you get 4EI U1 by L1. At the second end you will get 2EI U2 by L1. So the member end force P1, which relates directly the moment value. So the moment is 4EI theta. Instead of theta, we are going to use the member end displacements because here the theta refers indirectly to member end displacement. So 4EI U1 by L1 plus the other end, it causes 2EI U2 by L1, U2 by L1 plus all other parameters P3, P4, P5, P6 are 0. So for P3 it is 0, P4 it is 0, P5 it is 0, P6 it is 0. Next one we are going to write for P2. So you are going to apply a unit rotation here, theta equal to 1. First case you are applying unit rotation, theta equal to 1 here. Now it is here. So the moment at this point is 4EI by L, the other end is 2EI by L. So the first span, in the first span, you are applying a unit rotation theta equal to 1, so that it will create 4EI U2 by L1 here, and here 2EI U1 by L1 here. Okay. In the first case, 4EI U1 by L1, 2EI U2 by L1. The second case, 2EA U1 by L1, 4EA U2 by L2. So 2EI U1 by L1 plus 4EI U2 by L1. Both the member end properties are referred with only L1. For the P1 and P2 for only L1. Other parameters are 0. So you continuously have to write for P3. P3 is for L2, member L2. At the left end, it will cause 4EI. What is the member end displacement coordinate for P3? It is U3. U3 by the length is L2. At the far end, it will create 2EI. The member end coordinate is U4 divided by the length of the member is just L2. Actually, I done one mistake. So it is correct, but for the totally 6 parameters is there, no? So we have to write here, that is 4, the third coordinate 4EI U3 by L2 plus 2EI U4 by L2, because this column is referred to U3 and U4. So this is referred to U1, U2, U3, U4, U5, U6. All other parameters are considered to be 0. So the first two parameters should be mentioned as 0 because we are going to formulate a matrix with this set of equations. So this is also the first two values are 0. Here 2EI U3 by L2 plus 4EI U4 by L2 and others are 0. In the next case P5, as usual, P5 is represented with U5, P6 is U6. For the P5, it is 4EI by L. Far end, it is 2EI by L. When coming to P6, it is 4, and far end is 2. So you have to put 0 up to P4. Okay, P5, it is 4EI by L. U5, L is L3 plus 2EI U6 by L3 for the span, third span. So P6, 0 plus 0 plus 0 plus 0 plus, now it is coming left side 2, right side and 4. U5 by L3 plus 4EI U6 by L3. So now I am going to formulate one matrix P with the um, matrix in connection with U. So you have to separate U terms outside, and keeping the values, other values inside, we can formulate one matrix. So give some space for accommodate all the values P5, P6, because it will be like 6 by 6 matrix. So I'm going to write 4EI by L1, 2EI by L1, here 2EI by L1, 4EI by L1, and for other terms, 1, 2, 3, 4, 5, 6 terms will be available. So after this it will 0. For the third and fourth coordinate, the second span is active. So 4EI by L2, 2EI by L2. For the fourth coordinate, 2EI by L2, 4EI by L2. All other parameters are 0. Okay. I am separating only the U terms, the member end displacement. P5 and P6 is for the last span. So this 2 by 2 matrix will be active. 4EI by L3, 2EI by L3, here 2EI by L3, 4EI by L3. You just close the bracket and mention all the U terms. U1, U2, U3, U4, U5, U6. So the bracket should be like this for varying parameters. For the given loading, the P can be varied, U can be varied, but for the given structure of the given span, this matrix will not vary. That's why we are putting box type of bracket. Okay, so if I arrange this, P equal to totally K is global stiffness matrix into member end displacement, where K equal to assemblage of member stiffness matrix K1 assembling in a diagonal manner. So each K1, K2, K3 will be in 2 by 2 matrix format, that is 4EI by L, 2EI by L, 2EI by L, 4EI by L. So each K will be in this format. So I am not mentioning with the K1, K2 because I am putting generally length L instead of putting L1, L2, 3. So each K1 represented 2 by 2 matrix, so 4 by 4 and finally 6 by 6. So you keep this is equation number 3. Equation number 3. Previously we have two equations. So I want to remember the first equation is U equal to A into delta. The second equation is W equal to A transpose P. So I am going to write U equal to A into delta. So this is our first equation. Then W equal to A transpose into P is our second equation. Now we get P equal to K into U. This is our third equation. So 1 and 2. So now you have equation 1 to substitute equation 3. So substitute equation 1 in 3. So P equal to K and A and delta. How it comes? So you substitute U equal to A into delta. U equal to A into delta. So we have another equation, that is fourth equation, P equal to K delta. So now you revise that second equation, W equal to A transpose P. Okay. You substitute equation 4 in 3. Substitute equation 4 in 3 because we have P terms but we have some relation for P. So for the simplification, we are going to convert all the equation in terms of K into A, simplified form because it will not change for a particular problem. So we are going to convert all the items into K, A and other. So W equal to A transpose, it is in square bracket, and P is equal to Ka delta. Okay. K and A and delta. Okay. And these three are constant for a particular span or particular given problem. So we can replace this as J, which is structure stiffness matrix, which is structure stiffness matrix. So J referred to structure stiffness matrix. So it is a very important parameter. J equal to structure stiffness matrix. Then I'm going to write here. So for a given problem, we need the bending moment value. Our ultimate aim is to find bending moment value. The bending moment value formula. Okay. Here I am going to continue this equation number 5. I just convert this equation delta equal to J inverse into W. J inverse into W. I just rearranging this term delta equal to J inverse coming to this side J inverse into W because W is the joint load which can be calculated with the given problem. W is the joint load which can be calculated with the fixed end moment values which I have discussed in the first slide. Available loads are calculated for fixed end moment value and net fixed end moment value we should calculate and consider the opposite sign for the net fixed end moment value which is the joint load. So in this formula, we know W. If you calculate J inverse, then we can find delta. Okay. And with the available data of delta, you can find member end force P. You can find member end force P. With the member end force value, you can find the bending moment. First of all, I am going to write the step-by-step procedure in reverse wise. We need bending moment. The bending moment values can be calculated as the formula mu plus P. What is the new term? Mu represent definitely fixed end moment. Definitely fixed end moment. And you will have the fixed end moment value for if it is the B member. You will have the fixed end moment here, 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 here at both the ends. At both the ends you have totally 6 values. So mu1, mu2, up to mu6 you will have this one. Similarly, the p-value also you have p1 to p6. Okay, you can add the fixed and moment value with member end force, you will get moment equation. So what is the formula for member end force P from this derivations? P equal to K into A into delta. Okay. Okay. What is the here for a given problem? A can be easily formulated. K can be easily formulated with the 4EA by L 2EA by L formula. A can be easily formulated initial step. So delta should be found out. How the delta can be found out? Delta equal to J inverse into W. So how J can be found out? So J can be found out using A transpose K into A. So how K can be formed up? By diagonally arranging the member stiffness matrix. How A can be formed? So by applying a unit rotation at the joint. Let me explain the next slide. So our problem with the three spans example representation is given. For this we have to find first step to find A matrix. After the fixed and moment calculation, first step to find A matrix. How it can be find? So what are the possible location of applying the deflection? The fixed end will not carry any deflection, so it is not meaningful to apply delta at this joint A. So we directly apply delta 1 and delta 2 and delta 3 here. So for that, we first apply a unit rotation theta equal to 1 at this support, at this first joint. So this support will be rotating like this. So that here the rotation is 1, at this end the rotation is 1, all other member and coordinates the rotation is 0. Okay, this is not actually overhanging, this is purely simply support. The next step, it is actually theta 1 equal to 1 or u1 equal to 1. You can consider like this. The next step, at the next possible joint, you apply u2, sorry, theta equal to 1, so that it will rotate like this. So the rotation at both the ends are 1, other values are 0. And next, at the last simply supported place, we apply theta equal to 1 unit rotation, because we are going to formulate stiffness matrix K. For that, the basic formula is moment per unit rotation. That is, we have to apply unit rotation and find the effect. So at this end we are applying means here we will have one value. All other joints member end parameters are considered to be fixed. That is why it is 0. Now assemble this row of values in the column wise. Assemble this row of value in column wise. 0. I am going to assemble this row of value 1 1 0 0 0 column is totally 6 values are there, because we have 6 member in coordinate and 6 member in displacement. You assemble this second row as the second column 0 0 0 1 1 0, and you assemble the third row as the third column 0 0 0 0 0 1. Okay, so now compare with the values. Here we get the same matrix 0 1 1 0 0 0 0 0 0 1 1 0 0 0 last one 0. So we get same value. So this is the procedure how we can formulate A matrix for a given problem. For example, if you are given mm, with this beam, first one, all three supports are the possible location of applying delta 1, delta 2 and delta 3 so that we can apply unit rotation at each support. So first I am going to apply the rotation here. Okay, so theta equal to 1 so that the left end will be the unit quantity we have, so other end 0. For the next support, the intermediate support, you apply a unit rotation so that here 1 and 1, others are 0. For the last support, you apply a unit rotation, so theta equal to 1 so that here 1, others are 0. So you assemble in column wise, that is 1, 0, 0, 0, 0, 1, 1, 0 and 0, 0, 0, 1. If you are expert in this, you need not draw these diagrams. You can directly uh, formulate the A matrix. At the fixed support, there is no joint displacement. You should keep in mind that at the fixed support, there is no possibility of joint displacement. Only the member end coordinate should be mentioned here. That is P1, U1, P2, U2 should be mentioned for all the member ends. But the joint displacement is not possible at the fixed end. So you keep in mind, again I am repeating the steps, the first steps for the given problem to find the fixed end moment. The second one, A matrix. Third one, K matrix. Fourth one, that is mm, J matrix, that is A transpose K into A, and fifth one J inverse, and sixth one from the fixed end moment value we have to form the joint load matrix, because opposite to the fixed moment value is the joint load. Next one, delta equal to J inverse into W. Okay, so you should properly put all the brackets corresponding to this variable as well as the stiffness matrices. Okay. Next one, seventh, P equal to, the member end force P equal to K A into delta, Ka into delta. Finally, the moment equal to fixed end moment. I am representing with mu, the fixed end moment plus P, fixed end moment plus P. So you will get 6 moment value, M1 to M6 at the ends. You have to draw the bending moment diagram as in the case of slope deflection and moment distribution method. So this is all about the methodology of stiffness matrix.